So yeah, let's get started, guys, without any further ado. Now, as mentioned today, we'll be going with the first demo, again, the actual class itself, which is going to act as a demo as well. Networking fundamentals, one of the most important prerequisites for cybersecurity. Okay, because you need to understand what IP addresses are. Because when we work in cybersecurity, when we go through logs, we notice a lot of numbers which are called as IP addresses. So it's important to understand what those IP addresses are, how you identify what are the different categories of IP addresses. Okay. JP, I hope you can hear me as well and the screen is visible. Per- Perfect. Right. So you talk about networking fundamentals, guys. There are three important definitions to know first. What is networking? What are networks and what are hosts? When you talk about networking, this is the practice of connecting information devices with each other. Okay, so when you have an organization, in that organization, you have multiple devices. You have routers, you have servers, you have client operating system devices, you have firewalls, you have IDS, IPS, intrusion detection systems, and intrusion prevention system. Okay. You have again load balancing servers, FTP servers, DNS servers. What's again all sorts of servers. So again, having that connectivity so that all of these devices can communicate with each other, they can share the resources with each other is the concept of networking. Okay. And when you have a group of devices, the collection of that group of devices, interconnected devices, is called as a network. And each individual device or each individual information system in that network connected is called as a host. So your printers, routers, again, computers, mobile phones, IP cameras, your web servers, your different sorts of servers, your smartwatches, etc., etc. All of these individually is known as a host. Okay. Now, just like how we humans communicate with each other and we address each other with our respective names, similarly, these devices also have an identification. That identification is called as an IP address. So each host on the network has a unique identifier known as an IP address. Okay, and these IP addresses allow for communication to occur between these hosts. Okay. So when these were invented by the US military in the late 1950s or so, there were multiple versions of it. IP version 1, IP version 2, IP version 3, so on. All of these were quite experimental. They didn't work out successfully. What properly worked out or panned out was IPv4, Internet Protocol version 4. And even in today's world, we are still using IPv4 addresses. Okay. So again, the IP address that we use today is called IPv4 address, Internet Protocol version 4. And this IPv4 address has a few important unique characteristics to it. Okay. So firstly, it's a 32-bit address. What I mean by 32-bit address is that it contains 32 zeros or ones. A bit is the smallest data value a computer or any information system can hold. It can either be the value of 0 or it can be the value of 1. Okay. And your entire IPv4 address is a 32-bit address. It contains 32 zeros or ones. Okay. And this entire 32-bit address again is divided in four equal parts. Okay. And each of that part consists of 8 bits, and that part is known as a octet. Okay, so octa in the sense 8. So your entire 32-bit address is divided in four 8-bit sized portions, which is called as an octet. And each octet here is separated by a dot symbol. So this is what your typical IPv4 address looks like in the language of zeros and ones. And this language is also commonly known as binary language. Okay, so there's 8 zeros and ones here. Then there's a dot separating the octet, then another 8 zeros, then a dot, then another 8 zeros, then a dot, then another 8 zeros. So 8 fours are 32 bits in total. So what we see here is the computer readable language. This is not easily understandable by humans. What humans understand are decimal numbers, numbers from 0 to 9. So this number 11000000 can actually be converted into 192. This number 10101000 is actually equal to 168. This number, all zeros, is simply 0. And this number, 000000, sorry, 00001010 is equal to 10. Okay. So now we'll be learning that conversion. How do you convert any binary number to a human readable decimal number? Okay. Any questions up to this point? JP, Omkar, there.
No, clear.
Right.
No.
So let's get into the conversion and I'll explain why this conversion is important as well in a minute. So when you want to convert any binary number to a human readable decimal number, there are two simple rules. So let's assume we take this number here. 10101010. Again, this is an octet, 8 bits in total. So when you want to convert any octet in this binary language to a human readable decimal language, step number one is you assign the power of 2 to each bit from right to left. Okay, so you start from 2 power 0 and go all the way up to 2 power 7. So the rightmost bit has 2 power 0 under it. Then you have 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, and 2 power 7. So from right to left, you assign the power of 2 power from 2 power 0 all the way up to 2 power 7. Okay. Once these values are assigned, then you multiply the lower value with the top bit and keep on adding it till the end. So 2 power 0 into 0 plus 2 power 1 into 1 plus 2 power 2 into 0 plus 2 power 3 into 1 plus 2 power 4 into 0 plus 2 power 5 into 1 plus 2 power 6 into 0 plus 2 power 7 into 1. So you multiply the lower value with the top bit and you add it to the next value. So multiply and add, multiply and add, multiply and add. And that way you get the decimal answer. So if we calculate this value now, anything to the power 0 is always equal to 1. That's a mathematical rule. So 2 power 0 is 1. 2 power 1 is 2 itself. 2 power 2 is 2 into 2. That's 4. 2 power 3 is 2 into 2 into 2. 3 times. That's 8. 2 power 4 is 2 into 2 into 2 into 2. 4 times. That's 16. 2 power 5 is similarly 32. 2 power 6 is 64. And 2 power 7 is 120. So now that you have these values, now you can assign them over here. 2 power 0 into 0. 2 power 0 is 1. So 1 into 0, that's 0. 2 power 1 into 1. 2 power 1 is 2. 2 into 1, that's 2. 2 power 2 into 0, 0 again. 2 power 3 into 1, 8. 2 power 4 into 0, 0 again. 2 power 5 into 1, 32. 2 power 6 into 0, 0 again. And finally 2 power 7 into 1, 128. And if you add all this up, 128 plus 32 plus 8 plus 2, you get the number 170. So 128 plus 32, that's 160. 160 plus 8, 168. 168 plus 2, 170. So when we humans read the number 170 as 170, the computer reads it as 10101010. Something like high frequency, low frequency, high frequency, low frequency, high, low, high, low. So when that exact sequence of frequencies flows through a computer, it reads it as the number 170. Okay. So this is how you convert any binary number to a human readable decimal number. Is that clear, guys? Any questions? Perfect. So if this is clear, I have two other numbers here, 01010101 and all ones. So if you have a pen and a paper beside you, I would want you to convert these numbers into decimal values and give me the answer for those. Take your time, no rush. I've written down the values here from 2 power 0 to 2 power 7. And these are the numbers 01010101 and all ones. You can answer in the chat box or you can let me know the answer.
First one is 85.
Okay, we have got one answer. First one, 85. Let's verify that. Any answers, Jacob? Okay, good. Okay, guys. So let's try calculating the first one over here. So again, same logic, 2 power 0 into 1, that's 1. 2 power 1 into 0, 0. 2 power 2 into 1, that's 4. 2 power 3 into 0, 0 again. 2 power 4 into 1, 16. 2 power 5 into 0, 0 again. 2 power 6 into 1, that's 64. And 2 power 7 into 0, that's 0 again. And if you add all this up, 64 plus 16, that's 80. 80 plus 4, 84. 84 plus 1, 85. And if you go for the next number, you have all ones everywhere. So you just add up all the numbers. 127 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And when you calculate that, you should get the number 255. Okay. So the reason I'm explaining you this binary to decimal conversion is because from the same conversion, we can get the range of IP addresses. So if I had to get the first IP, all I have to simply do is put all zeros everywhere. In every octet, I just need to put zeros. Okay. And when I convert that from binary to decimal, I simply get the first IP as 0.0.0.0. And if I had to get the last IP, the maximum I can get out of an octet is by putting all ones in it. And when I put all ones, I get the last IP as 255.255.255.255. So this gives you a logical understanding of why IP addresses cannot progress after the number 255. Because in an octet, when you put all ones, the maximum it can reach is 255, not more than that. Okay. So whatever IP addresses you notice in the world when you talk about IPv4 addresses, all of them would only have numbers ranging from 0 to 255 in each octet. And the logical reasoning is so and so. Okay. When you put all ones, the maximum it can go up to is 255. When you put all zeros, the least it can go up to is 0 itself. Okay. Now, if this is the first IP and if this is the last IP, how many IPs would we have in total, guys? Each octet over here has 8 bits. And each bit again has two possibilities. So 2 into 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 2, all the way 32 times. So if you had to calculate the total number of IPs, you would get it by the number 2 raised to the power of 32. And that would be a value of 4.3 billion IP addresses. Okay. So again, back then in 1950s or so, when IP addresses were invented, they thought 4.3 billion IPs is a very huge number because in 1950s you didn't have mobile phones. Hardly people had access to the internet. Only organizations had computers. Computer was a luxury in a small home. Okay. So but fast forward to 2024, every person has multiple devices. They could have a laptop, they could have a smartphone, they could have a smart TV, a smartwatch, and each of these requires an IP address. Okay. So thereby, when you talk about the world in 2024, 4.3 billion IPs would never have been sufficient, okay, for the entire population of 8 billion people. That's why these entire range of 4.3 billion IPs are again divided in various categories. There's public IPs, there's private IPs, and then there's classes, class A, B, C, D, and E. But before we get into that categorization, let's talk about the sequence of IPs. So we know this is the first IP, and we know this is the last IP. What about the sequence of IPs in between? Okay, how do the IPs progress one after the other? So to understand the sequence of IPs, there are two simple rules again. Rule number one is you always start incrementing from the rightmost octet. So what I mean by that is, for example, if this is my IP, first IP here, 0, 0, 0, 0, if that's the first IP. In order to get the next IP, all I have to do is increment the rightmost octet. Okay, so after 0, 0, 0, 0, you would have 0, 0, 0, 1, then 0, 2, then 0, 3, then 0, 4. So all you're doing is you're incrementing or increasing the rightmost octet, but with the value of 1. Okay, then you have 0, 6, 0, 7, 0, 8, 0, 9, 0, 10, 0, 11, goes on all the way up to 0, 2, 5, 5. After 0, 2, 5, 5, please note, you will never have a value like 0, 0, 0, 256. This is not possible. Okay, it's a wrong IP. It's an invalid IP. Okay, so once you reach the maximum value there, 0, 0, 0, 255, then that 255 cycles back to 0. And now the next octet increases by 1. That's rule number 2. After the rightmost octet is completely filled, when it reaches the maximum value, only then you move to the left octet. Okay. Now, after you move to the left octet, don't again directly jump from 10 to 0020. That would be wrong again. Remember rule number 1, always increment the rightmost octet. So after 1 0, you have 1 1 again, then 1 2, then 1 3, then 1 4, then 1 5, which goes on all the way up to 1 2 5 5. Then you have 2 0. So you see there's a pattern forming here: 0 0 to 0 2 5 5, 1 0 to 1 2 5 5, 20 to 2255. I've skipped a few IPs in between, okay, just to again write down a larger range. Then 30 to 3255, 40 to 4255, 50 to 5255. Like that, the cycle keeps on repeating. And somewhere down the line, you would have 2550 to 255255. Now, once both these octets are filled, what happens? They cycle back to zeros again, and the left octet increases by one. So you have 00 again. So again, 100 to 10255, 110 to 1255, 20 to 2255, 30 to 3255. Like that, the cycle repeats again, and you have 2550, which goes up to 255255. Then this one changes to 2. Okay, so again, this is the next pattern: 000 to 0255255, 100 to 1255255, 200 to 225555, 300 to 325555, 400 to 4255255, 500 to 525555. Like that, the cycle keeps on repeating. And somewhere down the line, you would have 25500 to 255255255. Okay. Now, once all these three octets are filled, this zero now changes to one. So whatever cycle repeated all the way from 0000 to 0255255255, same cycle repeats again from 1000 to 1255255255, 2000 to 2255255255, 3000 to 3255255255, and similarly 255000 to 255255255255. Here's the first IP, and here's the last IP. Now, definitely, I did skip a lot of IPs in between, but again, I hope you got the sequence. So, okay, so that is how IPs progress one after the other. And if you start counting each and every IP, you would get approximately 4.3 billion IPs that way. Okay, so that entire 4.3 billion IPs again are divided in various categories. Okay, so there's something called classes: class A, B, C, D, and E. And again, in each class, you have two subcategories: public and private IPs. So class A has public and private. Class B has public and private. Class C also has public and private. Class D and Class E don't have any private IPs in them. All of them are public IPs itself. Okay. But what are these public and private IPs? What are these classes? So let's talk about that now. Again, when you talk about public and private IPs first, this simple diagram can give you a better understanding. So now let's assume this is your home network, guys. Oh, before that, any questions or doubts up to this point? Jacob, Omkar, or then?
No.
Okay. So let's assume we take our home network's example itself. So in our home network, we have multiple devices. So we might have a Wi-Fi router, and to that Wi-Fi router, we might have all our other devices connected. Your laptop, your smartwatch, your smartphones, your smart TVs, whatnot. All of these are wirelessly connected to your Wi-Fi router. Now, when any of these devices wants to communicate with each other, here they use something called private IPs. So this is your private network, which is also commonly known as an intranet. Okay, intranet is your local private network. So when you want devices communicating in a local private intranet, there you use private IPs. So private IPs are the IPs assigned to each device in a local network. Okay, a unique IP is assigned, a unique private IP is assigned to unique device, and these private IPs allow for communication to occur between these devices. But when these devices want to communicate with the internet now, you can't directly communicate with a private IP. You need a public IP for that. So public IP is an IP assigned by the ISP, Internet Service Provider. So in India, you might have ISPs like Act Fibernet, Airtel, BSNL, etc., etc. In US, you have ISPs like AT&T, T-Mobile, Verizon. All these are ISPs in US, and these ISPs provide you a public IP. So if you carefully observe, your router gets a cable from outside the house, an optical fiber cable or an RJ45 cable, whatever. That cable carries the public IP assigned to you by the ISP. Okay. So when any of these devices wants to communicate with the internet, let's say a website like google.com, they will always require a public IP for that. So if my laptop wants to communicate with Google, it first sends a packet from its own private IP to the router's private IP. The router then again allows you to communicate between two different networks. Okay, it shifts the packet from the private interface to the public interface, and then it uses the public IP to send the traffic outside your network on the internet. And with that public IP, the packet travels to the internet web server. So whenever there's communication happening over the internet, over the public network, you need the public IP. In your local area private network or the intranet, you need the private IP. Okay. So public IPs are IPs used to communicate over the internet, okay, over the public network. Private IPs are the IPs used to communicate in your private network or the intranet. Okay. Intranet private IPs, internet public IPs. That's an important point. Okay. So defining them again, public IPs are the IP addresses, globally unique addresses, which are used to identify devices on the public internet. They're allocated by the ISP, they are routable over the internet, and they're, again, you can check them with the simple command, what is my IP? So you can just go to your browser, and in your browser, you can search the query, what is my IP? And that shows you your public IP. So right now, my system or my router is getting this public IP from my ISP. And if I want to know what my ISP is, I can select this link as well. I can click on this link, and this shows me my ISP also, Beam Telecom. Okay, shows my city, my region, and my country as well. From where is this ISP allocating an IP from me? Okay. On the other hand, when you talk about private IPs, these are the IP addresses used within private networks, home network, office network, organization networks. So for your local communication, you use private IPs. These are not directly accessible from the public internet. So you cannot use a private IP to connect to the internet directly. You need a public IP for that. Okay. Private IPs only allow devices within the same local network to communicate with each other. So in your own home network or in your organization network, when one device wants to communicate with the other device, then you don't need a public IP for that. A private IP is sufficient. Okay. And if you want to check what your private IP is in your Windows system, you can open up the command prompt. And in the command prompt, you can run the command ipconfig, Internet Protocol Configuration. And you can see this is my private IP here, 192.168.0.5. Now, why am I getting specifically 192.168 here? Why am I getting specifically 49.204 here? Again, there's ranges for each public and private IP. Okay. We'll talk about those ranges in the next class. Okay. So again, for each class, there's a unique range. And in each of those classes, there's a range for private and public IPs. So it's very important to remember these ranges, guys. But don't get confused. Don't worry. Seems a bit complex, but there's an easy trick, a very easy trick to remember all these numbers. Okay, so we'll talk about that in the next session. So in the upcoming sessions, we'll talk about these ranges. I'll specify what a class is. I'll explain what all of these classes are. What's the necessity for 5 separate classes? Okay. And we'll talk about some important protocols as well. What is subnet mask? What is DHCP protocol? What is DNS protocol? We cover all this in the next session in tomorrow's class, which will be the last class for networking. Okay, so yeah, this is a brief intro on what the classes are going to be like. Today we have covered part one of networking. Tomorrow we cover part two. And day after tomorrow we cover the lab setup installation. How do you install a practical lab for the upcoming sessions? Okay, so this is going to act as a demo for you, just in case if this is your first session, guys. Any questions, Jacob, Omkar, Uday?
No, sir.
Perfect. So we can connect back tomorrow at the same time, guys.
I have one more question, sir. Actually,
Yes.
8 o'clock you have a break, right?
8 o'clock? No, there is some time left for 8 o'clock batch because there is one ongoing batch running right now. So that will
Okay.
complete in a week or so. And after that, we'll start the 8 p.m. batch. So it will take a while.
Okay, because office HR giving time is finding little difficulty. That's why I'm just thinking. Today also I
Oh,
joined 10 minutes later. And
no worries. Again, we'll start the session by 7:10 or something, 7:10, 7:15. So that again, if you're late as well, you can join the session. But if it's too problematic, you can wait for the 8 p.m. batch as well. We'll be starting that in a week or two. Okay.
okay, okay.
Yeah. That's that. Nothing
Well,
further.
let me talk to my manager then. I'll Okay.
Sure, sure.
Meantime, you tell me what is that hardware. I spoke to you yesterday on the hardware part. Let me put a mail, so I'll have when I'll
Sure.
I'm doing it.
Right. Sure. Okay,
Oh,
that's that. Nothing further for the session today, guys. We can exit the session and connect
sure,
back tomorrow at the same time. Bye-bye.
sure, sure. Thank you.
Thank you.